Hello students! Welcome back to our science video. For today's lesson, we will cover both horizontal and vertical motions. At the end of this video, learners are expected to describe uniformly acceleration motion and problems using UAM equations. Second, describe the motion of freely falling objects and solve free-fall problems using UAM equations. Uniformly accelerated motion or UAM. Uniform acceleration means a constant or a steady acceleration. Since acceleration is a vector quantity, uniform acceleration denotes that both the magnitude and the direction of acceleration stays constant. Wherein, uniformly accelerated motion occurs when an object experiences an increase or decrease in velocity at the same rate throughout the motion. Both situations are showing uniformly accelerated motion. By this, let's differentiate uniform motion with uniformly accelerated motion. Uniform motion. The figure below shows the car moving at constant velocity. It means that at each second, the car covers equal distances as seen in the equal spaces between each car image. The red arrows that represent velocity also have equal lengths, which mean equal magnitude. It illustrates that the velocity of the car is the same throughout the motion. Since there is no change in velocity, acceleration is zero. On the other hand, let's discuss uniformly accelerated motion or UAM. The figure below shows increasing distances between the car images. It shows that the car covers an increasing distance per second. The red arrows are also of increasing length and the increased amount is the same. This signifies that the car experienced a uniform increase in velocity. However, the violet arrows are all equal in length while pointing towards the positive direction. It means that the car is moving with uniform acceleration in the positive direction, or also called as positive uniform acceleration. The figure below also experiences uniform acceleration, but as seen in the image, the red arrows as well as the violet arrows are pointing in opposite directions. The velocity, as shown by the red arrows, also decreases based on its decreasing length, but all of its points in the positive direction. These violet arrows pointed in the opposite direction, which means that the car has a uniform but a negative acceleration. A negative acceleration is often called as deceleration or a retardation. These are the different UAM equations that can be used to compute distance and velocity. Let's apply one of the UAM equation in this sample problem. Starting from rest, a brick slides along a straight line down a polished roof with a constant acceleration of magnitude 4.9 meter per second squared. How fast is the brick moving when it reaches the edge of the roof 0.90 seconds later? To answer this sample problem, let's follow these steps. Step 1. Identify what is required to find in the problem. You are asked to calculate for the final velocity of the brick. Step 2. Identify the given in the problem. The initial velocity, acceleration of the brick, and the time of travel are given, wherein initial velocity is equal to 0, acceleration is equal to 4.9 meter per second squared, and time is equal to 0.90 seconds. Since the question is asking for how fast the brick reaches the edge of the roof using the given quantities, we can use this working equation. Final velocity is equal to initial velocity plus acceleration times time. Step 4. Substitute the given values. Final velocity is equal to 0 plus 4.9 meter per second squared multiplied to 0.90 seconds. In performing the equation, the final answer will be final velocity is equal to 4.41 meter per second. We're done with objects moving in a horizontal motion. Let's proceed with objects moving in a vertical motion or freely falling bodies. Free fall motion has baffled scientists in ancient times. During the 4th century, Aristotle suggested that heavier bodies fall faster than lighter ones. 19 centuries later, Galileo proposed a contrasting idea about free fall motion, wherein, according to him, all objects experience the same downward acceleration when neglecting the effect of air resistance. Galileo Galilei is an Italian physicist and astronomer who has a wide range of contribution in science. One of his most important contributions is his formulation of both concepts and calculations governing free fall motion. He used a systematic experiment using inclined planes. In his setup, he rolled balls in an incline and measured the distances it covered at each successive interval. He used an inclined plane for him to reduce the acceleration and accurately measure those distances. Free fall motion is any motion of an object or body solely influenced by gravity. It means that the effect of air resistance is negligible, and therefore has an insignificant effect on the falling object. On Earth, however, free fall is an idealization since there is always some air resistance that will also act on the object or the body. Galileo used varying angles of inclined planes which helped him formulate the concept about free fall motion. The last setup includes rolling a ball in a vertical incline which produces a condition similar to freely falling object. To clearly understand this, take the next situation as an example. Suppose that a person stood high on a cliff and dropped a rock from that height. Assume also that velocity of the rock was measured at each second while it falls. For this situation, the effect of air resistance is negligible, and only gravity acts on the rock. A rock drop from a cliff has increasing velocity at a uniform rate, given that air resistance is neglected. In addition, the downward direction is considered as the negative direction, while the upward direction is considered the positive direction. We can calculate the acceleration of the rock using the equation below. Since air resistance is neglected in the example, the given equation has a uniform rate, wherein both equations will give the same value of acceleration, which is negative 9.8 meter per second squared. Air resistance, or sometimes referred to as air friction, is a frictional force which opposes the motion of a falling object. Thus, its direction is always opposite to the direction of the object's motion. It increases with the speed of the object. The faster the object is falling, the higher the air resistance. It also increases with the surface area of a falling object. With air resistance, acceleration throughout a fall gets less than gravity, because air resistance affects the movement of the falling object by slowing it down. How much it slows the object down depends on the surface area of the object and its speed. Based on the example, skydivers use parachute with a large surface area to slow down their fall. How about when a hammer and a feather are dropped at the same height? Which will reach the ground first? Does mass affect the acceleration of a falling body? To test if the concept of free fall is true, the same experiment was done by an astronaut David Scott on August 2, 1971. This was done on the moon during the end of the last Apollo 15 moonwalk. The hammer and the feather fell at the same time with exactly the same acceleration, because moon has essentially no atmosphere. Therefore, there is no air resistance that opposes the motion of falling objects. A hammer falls faster than a feather if there is an air resistance. However, once air resistance is removed, both objects will fall at the same rate. These are the different free fall equations that can be used to compute height and velocity. Based on the illustration, an object dropped from rest, thrown downward with an initial velocity, or thrown upward experience free fall motion. Let's apply one of the pre-fall equations in a sample problem. A student accidentally dropped her pen from the second floor of the school building, which is 5 meters from the ground. How fast is it moving when it hits the ground? To answer the sample problem, let's follow these steps. Step 1. Identify what is required to find in the problem. You are asked to calculate for the final velocity of the pen. Step 2. Identify the given in the problem. The initial velocity and acceleration due to gravity as well as the height are given, wherein initial velocity is equal to 0, gravity is equal to negative 9.8 meter per second squared, and height is equal to negative 5 meters. Since we are looking for the final velocity, we can use this working equation, since initial velocity, gravity, and height are given. Final velocity is equal to initial velocity plus 2 times gravity times height. Substitute the given values. Final velocity is equal to square root of 0 squared plus 2 times negative 9.8 meter per second squared multiplied to negative 5 meters. In doing the working equation, the final answer will be final velocity is equal to 9.90 meter per second or negative 9.90 meter per second. Thank you for watching. Do not forget to subscribe for more science educational videos by clicking the notification bell.